Assalamu alaikum everyone. Today we are going to conduct lecture number 21, and the topic of this lecture is arithmetic instruction. This is going to be third lecture on arithmetic instruction. So let's proceed to the topic. Okay, we are going to start our multiplication instructions, and there are three multiplication instructions which we are going to study in this lecture. The very first instruction is MUL or MUL. MUL is mnemonic for multiply instruction, and this multiply instruction is for unsigned numbers as it is written in this bracket. Format of this instruction is very simple. MUL and the source operand. MUL as is source operand. And what is going to happen in the back hand process of this instruction, so whatever the source operand we are going to use in this format, that source operand is going to multiply with A register or AL register, and we know that multiplication can be uh, of two cases. In first case there can be 8-bit multiplication, in another case it could be 16-bit multiplication. So SAT means a source operand of 8-bit, so it is going to multiply whatever the value which is present in the AL. So we must save one of the number which is supposed to multiply in accumulator register or AL register in case of 8-bit, and other 8-bit register or other 8-bit operand is going to be used indirectly in MUL instruction. So AL, which is priorly stored, and asset, which is given in the instruction, both will multiplied, and since both are 8 bits, so maximum number of bits which may appear in the result could be double. That means 16. So that is why the complete result is stored in 16-bit register, which is AX. It's important procedure, and I hope at this stage of your studies you must know that when you multiply two 8-bit numbers, so maximum result can appear in 16 bits, so we are going to target the 16 bits. So that is why the complete result will store in a 16-bit register, which is AX. Furthermore, there could be a second case in which we are performing multiplication of 16-bit number. So first 16-bit number will be stored priorly in AX register, and others S16 or the source operand of 16-bit will be given in the multiplication instruction. So those 16-bit number will multiply, and the maximum result could appear in 32 bits. This time we need a 32-bit register. But in 8086 or 8088 microprocessor, we don't have any 32-bit register, so we will be using two separate registers, DX and AX. DX will hold most significant bytes, 16 most significant bits, and AL will hold low or least significant 16 bits. So this is how multiplication will performed. There could be some flags which can get affect, like overflow and carry flag. They are mentioned up here, and then there could be number of bits of status register which are undefined, so those are also mentioned here. Okay, that was all about unsigned multiplication. So we were dealing only with the positive numbers. Let's deal with the negative numbers as well, or integer type numbers. So the instruction which is going to use will be here IMUL or integer multiply, and that is for signed numbers. So, and instruction format is almost similar to MUL S, so it will become IMUL S, and there could be two cases like we saw in MUL scenario. So in IMUL there will be also two cases, 8-bit multiplication and 16-bit multiplication. Rest of the procedure is almost identical, so I'm not going to discuss, and we are just going to see in emulator example. Same flags which are again get affected and which are not affected, both are mentioned here. Okay, like in addition and subtraction instructions, we saw in case of BCD multiplication we may have some adjustment requirement. So in case of multiplication, when we are multiplying to BCD numbers using hexadecimal numbers, so we may need some adjustment, and that adjustment is performed using this command, which is our third command in multiplication, that is AAM or adjustment AL for multiplication. And the format is simple, close to mnemonic, AAM, and that is the operation, and that we're gonna discuss in emulator clearly detail. But one can see that AL will be divided by 10, and there, once we know that whenever a number is divided by any number, there are always two results. One is quotient and other is remainder. The quotient will go to the AH and remainder will go to the AL. That thing will clear once we are going to deal with this example. So let's proceed to the example. Okay, let's perform a MUL example. We take two 8-bit number MUL and two 8-bit numbers. For example, we're gonna multiply 78 by 12, so that would be what result should be 12 7 okay, that should be 936. Yes, that should be 936. So that is the result in decimal. Let's convert them into hexadecimal. So 78, what it would be if we convert it into hexadecimal, it will be 4e. Yes, 4e, that should be 4e. I hope you can perform these conversion yourself. I'm just converting it directly. 12 should be directly 0c hex. There is no confusion at all. And if we multiply, equals to 936, and if we're gonna press 936 here, so that would be what, 3a8. Yes, so the result should be what, 3a8. I have just performed this conversion. I hope you can do it yourself, so I'm gonna use it in the program. Move first number, that is 78, and we're gonna do it 4e. Yes, 4e hex, and then move another number stored in P, so 0c hex, and we're gonna multiply MUL bx. Okay, no, sorry, these were 8 bits, so I'm using 8-bit register MUL bl. Yes, so let's see what is going to happen. I'm sorry, I just press run, so program is completely executed in one go. I wanted to do it in steps, so single step, 4e is here, 0c is here, and another, so 0338, which is exactly what we were expecting. So in this way we can perform multiplication using MUL command of 8-bit operation. I hope this point is clear. Okay, let's perform 16-bit multiplication using MUL command. So let's consider a number 16-bit which is moved in AX, for example F8 hex, and I hope you can understand the most significant bit here is F, which means it should be 1, so it is a negative number since it is a signed integer, remember. Okay, we are not considering right now signed integer, so we are just dealing it as a unsigned number. So next 8-bit number is F257 hex, and we're gonna multiply them, so MUL px, so it should be what, 16-bit number, so both are getting multiplied, so result should be what, result should be 32-bit. so result cannot store only in AX because AX is 16-bit, so we do need an extra register here, and that would be DX. So let's see the result. Okay, what is it? Okay, we missed 0 prefix because we were using, okay, now evaluate it. So single step, that is gonna be double F8, okay, that is right, then F257, and now BX, it will multiply with AX, and we will have a 16-bit result, sorry, 32-bit result, and that will be what, look, only 16-bit result is here, and most significant site is here, so result will be actually F2 for F6D48, and this is coming from dx and this is coming from ax. I hope this example is clear. Okay, right now we are going to multiply two integer number, so we will be using integer MUL or IMUL. So for example, our first number which is going to multiply it, and if we are doing just 8-bit numbers, so let's say we are multiplying -4 with okay, let me comment it. Yes, -4 times let's say -16, so that should be what, 64. That is in decimal, so let me convert in hexadecimal. So in hexadecimal it will be 0 1 0 4 only. No, not 0 4, it should be 0 0 0 0 1 0 0, but we will be writing in 2's complement, so that would become what, 0 0, sorry, 1 1 1 1 1 1 0 0, so that would become what, FC. Yes, so that is -4 in hexadecimal, and now we're gonna write -16, so 16 would be what, 0 0 0, sorry, 1 and 0 0. So but if we're gonna convert into 2's complement form, that would become 1 1 0 0 0. Yes, so it will become F0, so that is 16. So let's and we know that we will be getting result 64, so which should be what, it should be 64 16, that would be what, 40. Yes, that should be 40. So we will multiply FC with F0, we will get 40 or 40 in hexadecimal, while if we can consider these numbers in decimal, so these will be -4 times -16, and result should be 64. So let's do this thing. So move, let's say we are storing first number in AX or AL, and it is FC hex. Remember, we have to use this 0 prefix, so I'm using 0 FC. Move BL, next number is in, okay, this time we're gonna use CL, so next number is 0F0, and now we will be using IMUL CL. So CL will multiply it with AL, and it will have result equal to 40. So let's see. Single step, first value is loaded in AL FC. Single step, F0 is loaded in CL, and that is the result, 40. I hope you can see the result. So this is how. And one thing more, we can actually check flags. If there is any flag which is getting a fact, so there it will appear here. So this is how integer MUL is used. I hope this point is clear. Okay, now we are going to perform integer multiplication of two a 16-bit number. Let's say first number is FFF, and we will be multiplying it with, let's say, FFF0. So since it is integer, so this is also a negative number. See, we see here f, or most significant bit, is 1, so it is a negative number. Similarly, it is also a negative number, so when two negative numbers are getting multiplied, so result should be something positive. So we must know that result will not start with something positive number. So let's see. So move ax, which is first number, 0 4 times f, it is moved in ax move. Let's say we are using cx, so 0ff0. Next thing we're gonna use IMUL cx. So let's see what is going to happen with the result. Single step. Okay, ff is loaded in ax, 16-bit number. Triple f0 is loaded in cx, so we will have a 32-bit result, and that should be positive. Let's see. Look, the result is 0000010. So dx is also involved here in the result, as it clearly says that 0 0, sorry, in dx it is written 0 0, and in ax it is written 0010. That means we are having some number which is positive. I hope this point is clear to everyone. Okay, we are going to do example of AAM command or AAM instruction, which is adjustment after multiplication. We will be performing two numbers multiplication. Let's say first number is move ax comma 04 hex, next number is uh, 04 hex. So we are just multiplying 04 by 04, and remember in BCD or simple decimal 04 times 04 which should be 16, but in hexadecimal multiplication result will change, and since it is a 8-bit number, so I can use 8-bit register. And since in hexadecimal results will be different, so we will require some adjustment. That is why this command is used. So I have just used this command after this multiplication. So let's emulate single step. Number is loaded in AL. Good. Everything is fine as we were expecting, and then we press another single step 04, which is again. So now result is 10, which is supposed to be what, 16. So what we are going to do, we will be using this double AM command, which is about to execute. When I'm going to press this button, this command will execute it. So I'm pressing it. Look, 1601 is separated, 06 is separated, and that is thing which is called adjustment after multiplication. So when you multiply two BC numbers or two decimal number using hexadecimal number in emulator, you need some adjustment in 8086 processor. For that adjustment, AAM is used. I hope this example is clear. Okay, that's it from this lecture. Today we reviewed multiplication instructions. If you have any query, please note them down, and we will try to solve those queries in our online session. So thank you so much for listening.